Hello, my name is Lauren Ladd and I'm presenting my work, Predictive Indices from Prescribed Burns, How UAVs Can Improve Our Knowledge of Drought Stress Before and After Fires. This study was partially motivated by the Intergovernmental Panel on Climate Change's sixth assessment report. This report describes expected increases in temperature driven by anthropogenic climate change. Other projections include increases in the occurrence of extreme drought events, heat waves, and wildfires. While these projections differ depending on area of the globe, the report overwhelmingly points to alterations in the timing, spatial extent, and frequency of extreme weather events and resultant ecological impacts, such as loss of forest from extreme wildfire events. However, many of the Earth system climate models that we currently have fail to account for the mechanisms that drive ecological change and that are tied to our changing climate. As such, the physics and mechanisms of fire need to be further explored so that they can be incorporated into these models. Wildfires are a natural disturbance that drives regeneration, nutrient cycling, and forest density control in the western U.S. forests, as well as around the globe. However, with expected increases in the frequency and intensity of these disturbances, we might see more stand-replacing fires than what has existed historically, as well as increased fire return intervals that reduce the time allotted for regenerating trees to develop as seed sources. Some things driving these increases include climate change, which is expected to increase the average daily temperature in the western U.S., but there are also drivers that include earlier spring snowmelt, fuel accumulation, changes to the timing of precipitation events, and growing human populations in the wildland-urban interface. While these drivers are difficult to control, we do have the potential to monitor the extent to which they are impacting our forests at local scales. More specifically, we can use remote sensing to monitor conditions such as drought stress. In fact, several studies have demonstrated that pre-fire drought stress and moisture status is influential in determining how resilient trees will be in the event of a wildfire. One technique of examining these mechanisms that govern physiological change and facilitate this resilience to fire events is the use of laboratory-based combustion studies. This work is being pioneered by the Pyroecophysiology group at the University of Idaho and largely explores the relationship between fire intensity doses and mortality response of tree saplings. These controlled experiments allow researchers to gather validation data quickly for us to control specific variables of interest such as drought stress and fire intensity and to control sapling health conditions. Now, after reading about this work, I began to wonder, how will drought influence sapling mortality thresholds? And beyond that, can we sense drought stress using the multispectral sensors available on consumer-grade UAVs? We can already sense drought stress with satellite-based sensors, but these products are typically derived at a 20 to 30 meter spatial scale. And while this is useful for landscape-level drought detection, it might not be useful for land managers that are working at smaller spatial scales, particularly in the wildland-urban interface. And then beyond just drought detection, could information on drought stress of individual trees be used to inform land managers of pre-fire risk at smaller spatial scales? Thus, this drought indicator research had three primary objectives. First, develop a foliar moisture content indicator, or FMCI, using 10-band multispectral UAV imagery. Second, we want to examine the relationship between drought status and the fire intensity necessary to induce sapling mortality. Third, we want to evaluate the accuracy of this model in predicting foliar moisture content of mature conifer trees. For the purposes of this presentation, I will focus on the first objective, developing a foliar moisture content indicator. This FMCI is intended to mimic the normalized difference moisture index that is available using satellite-based sensors such as those available on Landsat. The study for this work was conducted on August 23, 2021, and used 61 Douglas fir saplings and 62 western white pine saplings. Each species was separated into 4 drought groups. The first was water to field capacity, which served as our control group. The second group was droughted for 12 days, the third group was droughted for 18 days, and the fourth group was droughted for 25 days. This variation in time without water allowed us to have a range of foliar moisture contents across both species. Then each drought group was split into 3 fire dose groups, as defined by fire radiative energy. The first group was our unburned control, which allowed us to examine if each level of drought would induce mortality without any fire. The second group was a low-intensity fire group that experienced 0.4 megajoules per meter squared. of energy, and the third group was a moderate intensity fire group with 0.6 megajoules per meter squared. Before the saplings were burned, an ASD spectroradiometer was used to collect 3 true spectral reflectance readings in the bottom 2/3 of the canopy and the top 1/3 of the canopy of each sapling. True foliar moisture content was also collected for each sapling by measuring the dry versus wet weight of 5 grams of needles. When planning this project, we expected indices like NDVI, which is an indicator of vegetation vigor, the near-infrared band, the thermal band, and the red edge bands to be potentially significant predictors of drought status. The PRI, or Photochemical Reflectance Index, was also on our radar as it has been used to detect soil moisture content using UAV-based sensors. Now, there are some clear areas of the electromagnetic spectrum where drought-stressed trees reflect light differently than healthy trees. In this graph, the drought-stressed saplings were 401 and 402, while the healthy saplings are the PSME 246 and PIMO 361, which both had above 150% foliar moisture content. We really aimed to capture those differences in reflectance in our model, and with access to 10-band imagery, the use of a single predictor variable would be a bit limiting, so we wanted to explore all possible bands and band combinations in order to provide the most robust model for predicting drought status. Following the burns, the foliar moisture content was calculated for each sapling. Then, the average ASD reflectance was averaged across the 3 values. Using the percent transmissivity value for the MicaSense dual camera system, I calculated the reflectance value at each wavelength within the bandwidth of the 10 bands on the sensor. This transmissivity function was then used to calculate a single reflectance value for each of these 10 bands. These bands are similar to those available on the Landsat and Sentinel sensors, as you can see in the figure on the right. Finally, the 10 bands were used to calculate multiple band indices such as the NDVI, the Normalized Difference Red Edge Index, and others. The foliar moisture content that we achieved from these drought groups covered a good range. Both species had saplings with a lower foliar moisture content, which were in the stressed group, and several saplings in the healthy group. In total, there were 85 saplings in the healthy group and 38 saplings in the stressed group. To build the predictive model of this foliar moisture content indicator, I used a random forest classification model. This machine learning method goes through a series of decision trees to classify each of the 123 saplings into 2 groups: stressed, which included saplings with less than 120% foliar moisture content, and healthy, which included saplings with greater than 120% foliar moisture content. To examine the full possibilities of using the drone for predicting moisture, I used the 10 bands available on the drone, as well as a thermal band, which is available on a separate camera, and several existing band ratios, which have already proven useful for remotely sensing other components of vegetation health. This totaled to 21 predictor variables. I ran the random forest classification model and examined the relative importance of each variable, as well as their correlation with each other, to get a final list of 4 predictor variables. When building the model, we did want to ensure that we weren't overfitting, so we examined the variable importance first and then the correlation between those important variables. We then chose our final list of predictor variables using the significant variables that had less than 70% correlation with each other. Now we had our final list of predictor variables, which included the blue band, a red edge band, NDVI2, and the Photochemical Reflectance Index, or the PRI. These 4 predictor variables were input into another random forest classification model and used to predict whether each sapling was either healthy or drought stressed. This final model resulted in an out-of-bag error rate of only 6.5%, with slightly more error in prediction coming from the healthy class. Following the model examination, we were pleased to see that a normalized difference vegetation index, a red edge band, and the PRI were significantly useful for predicting drought status. We were somewhat surprised to see the blue band as a significant predictor, although it does make sense as there were some noticeable differences in light reflectance in the 475 nanometer wavelength range that is covered by the blue band. Overall, this study demonstrates the potential of using a 10-band UAV sensor for predicting the level of drought stress of at least 2 conifer species, western white pine and Douglas fir, with 93% accuracy. In the near future, we hope to use this model for predicting individual tree drought status. This could specifically be applied in the wildland-urban interface, and could be applied across landscapes to identify areas and individual trees experiencing drought. Eventually, this model may be used for predicting wildfire risk and the risk of beetle invasion. In the coming months, we will continue to build upon this work by conducting the experiment on additional conifer species and evaluate how well the model applies to other conifers. We will also examine further band combinations that can be made using the 10 bands we have on our sensor. Further, we will test the accuracy of this existing model by applying it to mature trees with the hopes of incorporating it into fine-scale Earth system models. We also hope to apply this model to an experimental burn to predict pre-fire risk and examine the relationship between pre-fire drought status and post-fire physiological changes. Ultimately, we hope to use this foliar moisture content indicator as an early warning system for disturbances such as wildfire and beetles.